In a previous example, we calculated the mass moment of inertia of this shape that's a circle with a square missing from the center, and we calculated the mass moment of inertia about the center of this object. And we found that that mass moment of inertia was 11.22 kilograms per meter squared. And now in this example, I ask us to calculate the mass moment of inertia of this object about the axis A. So that's the axis going into the center of the board or through the board at this point A. And that's 0.75 meters from the center of this object. And so in order to do this, we don't have equations for the mass moment of inertia about any point in these things, especially if we look at our tables. We always kind of have them about the center, maybe occasionally about an edge, but not about an arbitrary point in the middle. So to solve this, we're going to have to use the parallel axis theorem. You might remember parallel axis theorem. In this case, I'll say the mass moment of inertia about that parallel axis A will be the mass moment of inertia about the parallel axis that I know it about. In this case, it'll be that center, the IO, plus the total mass of my object times the distance between those two axes, between 0 and A squared. So in this case, I know my IO, so that's easy. We did that earlier. Now I just need to calculate my total mass of this object. And we didn't actually do that earlier because we just needed the mass of the circle if it was full and the square if it existed. So in this case, to calculate the total mass, I will do the area density times the area of the circle, pi r squared, minus the area of the square. I'll just call that length maybe L squared. So that'll be my total area, or total mass, excuse me, and then times the distance between these two squared. We'll say d squared. And now I think I know everything to solve this problem. So mass moment of inertia about A will be the 11.22 kilogram meters squared about the center, plus the area density, 3.5 kilograms per meter squared, times pi r squared, 1.2 meters, minus that inside circle, 0.75 meters squared, and then times the distance between these two axes, which is also 0.75 meters squared. And the mass, the parallel axis theorem should always increase the mass moment of inertia of the object. And that's because it's always easiest to spin something around its center of mass. And as soon as you put that mass farther away from the center of rotation, then the harder it is to spin. And so here our mass moment of inertia after all this should be 19.01 kilogram meters squared. And that's our answer using the parallel axis theorem in calculating mass moments of inertia.